All right, good people. Welcome to video number 2 of Volumes of Solids of Revolution. We're going to have to read the problem very carefully so that we know the orientation of the revolution, so that we know exactly what is the shaded region. Sometimes they give you a picture like the one that's shown here. Sometimes they don't, and you have to build it yourself. Remember that we're finding the volume, and everything's going to be revolved around either a horizontal axis or a vertical axis. There's no revolving around a slant axis. So let's always look for keywords. Are we finding the volume? Is it being revolved? Is it a horizontal or is it a vertical line? If you are going to revolve it around an axis, and especially if that axis is not the x-axis, if it's another horizontal line, just remember that that line could be above the region, it could be below the region, but it's never going to be through the region, right? So I could revolve this shaded region, and I'm going to shade in the region in green here. This is the region that I'm going to revolve. It could be above, it could be about the line y equals 6, so it's going to revolve over and over. Or it could be revolved around this line, but we're never going to ask you to revolve it around a line that's in between, right? And I guess I should have switched colors, but I didn't. But yes, that's the key. And then always, let's draw our representative rectangle perpendicular to the axis of rotation. So once you know where the axis of revolution is, your rectangle that you're going to draw, your slice, is going to be perpendicular to that axis. Okay. If they don't do it for you, always draw the axis of revolution first, because that's going to kind of point you in the right direction of how you're going to set up stuff. We're always going to make a representative rectangle perpendicular to the x or to the axis of revolution. Perpendicular. We need to connect both ends of the rectangle to the axis. Let me try to fit this in to the axis. And then we need to label the distances big R and little r. Because as we're going to find out, and as we said in the last video, if we're doing a washer method, that means there's space in between. And so we need to cut out that hole, that circular hole in the middle. We need to cut it out. So we need to know what the big radius is and then what the little radius is. And we're going to practice that with example 1 right here. And then this is the formula that we're going to use, but this should be familiar because that's what we talked about here in the last video. But we'll emphasize it a little bit more when we get to that part. So this is an actual exam question from 2003 from AB1. It says, let R be the shaded region bounded by the graphs of y equals square root of x, okay, e to the negative 3x, yes, and the vertical line x equals 1. So they're showing me the region, they shaded it in. Find the area of R. Well, this is from a previous topic, right, where we need to find the area. Well, if I draw a representative rectangle, I know which function is the top and which function is the bottom. So then I can just set up my integral of one of these. So the top was square root of x minus the bottom was e to the negative 3x. And my thickness here is delta x. And I need to start, I don't know where I'm going to start, but I know that I'm going to stack all these rectangles. Let me do it in the right color. I'm going to stack all these rectangles like this, and I'm going to end at 1. So I know my ending limit of integration is 1. I don't know what the starting point is. So I'm going to use my calculator to figure that out. That's going to be important because we're going to need that value for doing the volume. So I go to my calculator, and let's see if I remember to pre-save. I pre-saved them here. Let's make the window small so that we can see everything. How about we go from -1 to 2, I'm sorry, -1 So 2 on the x, and then on the y, let's do the same. Let's just create a small window. Let's see what that looks like. All right, there's square root of x, and there's e to the negative 3x. What I don't have is a vertical line. Now, I cannot make a vertical line over here because a vertical line is not a function. However, if I go back to the graph, I could go to the draw menu. You don't have to do this. I'm doing this so that we can visualize it. And I can draw a vertical line, option number 4. And I think if I just type in 1, nope, I actually have to move it. Second draw vertical, and let's move it towards 1. There you go. So we're talking about this shaded region, right? Oh, but we just needed to find the intersection point. So I could have done that without setting this up. Okay, well, let's go to second trace, find the intersection point, option number 5. Move a little bit closer to where you think the intersection point. The first question is this blue curve the first curve you want to find the intersection for? Yes. Is the red curve the second function you want to find the intersection for? Yes. I want to take a guess, so press enter. And the intersection is 0.2387. Now I'm going to go ahead and save it. I'm going to pull up my x value here, and I'm going to store that in alpha A, just in case. But it is 0.2387. 0.2387. What do they want to see? If it's a calculator active part, they want to see the setup. We have the setup. But now we can use the calculator to figure out the full integral. Okay, so I come back over here and I can do, let me clear this, math option number 9 to do the integral. Remember, I saved my intersection value at A, and it goes all the way to 1. And then I think square root came first, and I have that saved in y1. Yeah, square root is saved in y1. So let's get back into here. Alpha trace, put the equation y1 minus, put the equation in y2, and then this is with respect to x. Bammo. There's my answer. That's the area of that shaded region. That's two-dimensional measurement, right? Area. 0.443. So that's about that. Great. Got that out of the way. Follow-up question. Using the same region, find the volume of the solid generated when R, that region, is revolved about the horizontal line y equals 1. Y equals 1. Y equals 1 is up here. So I usually make a little mark that says, hey, I'm spinning this around that axis. So I'm spinning this region around there. So the first question to ask yourself is there space between the shaded region and the axis? Is there empty space? Because if there is, that means it's going to have a hole. And if it has a hole, we're going to need the washer method. And so I can definitely see there's space in between the shaded region and my axis. That also means I need to measure 2 radii. And so I'm going to use my purple and pink because I think that's what I called capital R, my big radius, and then little r, I did it in pink, my little radius. And this is the way I usually do it. I tell students, find the axis of revolution. That would be this one. And draw a distance from here all the way to the outer edge of the shaded region, because that's going to be your big R. Start from the axis of revolution and draw a distance all the way until the inner part of the shaded region, the inner boundary. That's little r. Little r is the radius of the empty space, the hole. Big capital R is the radius of the whole thing. But we need to subtract the inside part. And so when I come back over here, what we're really doing is we're saying pi capital R squared minus pi little r squared, right? We're taking the area of the full solid revolution, but we're subtracting the hole that it creates because of that empty space in the middle. So then this is pi. Now wait, capital R. Capital R is this distance. It's a vertical distance. So whenever I measure a vertical distance, I always start and say top minus bottom. So in this case, it's going to be 1 minus whatever this bottom function is. And I believe it was e to the negative 3x. Minus pi little r squared. Well, little r squared, or little r, is this distance. And it's also vertical. And I find a vertical distance by taking the top value minus the bottom value. So top minus bottom is going to leave me 1 minus whatever this is. Oh, that's square root of x. This is the area function. This function finds the area of any one of those slices that we, so remember when we were doing areas of known cross section, there was like, can you identify the shape? Can you find the area formula for that shape? Can you create an area function and then take the integral of the area function? Well, that's what we just did here. We said, oh, there's space, so the shape is a washer, right? It's going to look like this with a hole in the middle. So I'm looking, that's not a donut, by the way, don't get hungry. This is what we're looking for. So big R, pi big R squared is finding the area of the whole thing, minus pi little r squared. Pi little r squared is finding the area of the whole. So we're subtracting that out. But we realize that by looking at this, I can figure out what big R and little r are represented by. And then now all I have to do is take the integral of this thing, pi 1 minus e to the negative 3x quantity squared minus pi. You know what? I don't even need to write both pi's. I can factor out a pi to the outside, right? If they both have a pi, I can just factor it out, and I have this setup. And I'm going to do that from 0.2387 all the way, I'm sorry, not all the way to a, all the way to 1. This is going to find the volume. We need to be detail oriented and figure out which way are we rotating that shaded space. Are we rotating it around a horizontal axis or a vertical axis? One is going to lead me to a setup that's in terms of x. One is going to lead me to a setup that's in terms of y, right? So if I'm spinning it around this way versus whether I'm spinning it around this way. And then the second thing is I need to figure out, do I have a disk where the shaded region is right up against the axis, or do I have a washer where there's space in between, so when I make a slice, it's going to look like a washer with an empty hole in the middle. This is the setup we need. Everything else the calculator is going to do, right? So I can put this into my calculator and get an answer. Well, let's do that. I guess we're already here, right? We might as well do it. So pi math 9. Remember, I saved my intersection value in a, not a to 7, a to 1. And then here I got to be careful. My calculator automatically opens and closes parentheses. So it's telling me whatever you want to integrate it, put it in there. But my expression has two sets of parentheses. So I have to do this. Open parentheses, 1 minus, I believe it was alpha trace 2. I think I went outside. Yeah, I did. I'm sorry. It should be here. Alpha trace 2. Close it and square it. Minus, I didn't open this one over here. Have to insert. There you go. I was trying to avoid that from happening. And then square root of x is saved in y1. And then I need to square that. And that's in terms of x. So here I have pi times the integral from that intersection point to 1 of 1 minus e to the negative 3x quantity squared minus 1 minus square root of x quantity squared. And when I press enter, this is the volume of that three-dimensional shape. And you might say, that's pretty small. Well, remember, the graph that we're looking at is trapped in between 0 and 1 and 0 and 1. So it's less than 1. And so when I do my whole volume of revolution, it's not going to be a big number. The moral of the story is the calculator is going to do most of the heavy lifting in terms of finding the answer. Your job is to set up the integral correctly. And that's going to be our practice in class the next time.